Hey everyone, today we are going to talk about the third category of AI attacks, data poisoning. AI models are only as good as the amount and quality of the data that they train on. Unfortunately, getting large amounts of quality data is expensive and time-consuming. To get around this, a lot of AI developers, such as OpenAI, take advantage of open source articles, maybe on Wikipedia or Google Scholar or Stack Overflow. And then often they're trained on Twitter data, Twitter now known as X. Well, this is great if you're an AI developer. It saves you a lot of money and time. However, it opens AI to a threat vector. So let's continue with the Twitter example. Let's say I, the hacker, want to shape the discourse around a person, place, or event. Twitter is estimated to be roughly 10% of bot activity. Let's say I, as the hacker, control 100 or thousands of these bots. I can generate mass amounts of data surrounding that particular topic, person, or an event. This will not affect how the model performs in most cases, except after the model is trained and deployed. If the user asks the AI a question on that topic that we poisoned, they will get disinformation. You can see how this is a very powerful tool. For instance, OpenAI. Let's say we could shape the discussion around a political figure. This is a very powerful and dangerous tool. So let's implement this attack with some code and demonstrate why we need to watch out for data poisoning. All right, let's add some metadata at the top of this file so it's easier when we come back or give this file to someone else that they can understand what we're doing. And we're doing an MNIST classifier, and here's two articles which I'm going to put on the resources that go in a little bit more detail about one, what is an MNIST classifier, and then about data poisoning. All right, let's do our imports. We're going to import TensorFlow, also Keras, import NumPy, all right, let's do our data. This is very similar to the other videos that we've done. Now, because this is just a demo, we don't want to spend all day watching the data load. We're just going to take the first 1,000 of each of these. Should make the video go by a little bit closer. All right, let's make sure this worked. Now we're going to import matplotlib so we can see what one of these data points looks like. And then also we need to change the images themselves so that they can come into the input layer of our model. Let's do this for the train and test images. There you go. You see the number 5, handwritten number. All right, let's define some functions. This is very similar to what we did in our previous video. We're just going to create a function that will help automate the setup for our model. And we're going to add some metadata so we can come back and remember what we did. All right, we're going to get a sequential model. And and we're going to define the layers. In that resource I put at the top, it goes in a little bit more detail about the different layers, or you can look back at our first video where we discuss how the layers let you do specific single bias Trojans. So we got that input layer, as you can see. That's why we had to change the shape of the image up there. All right, now we need to compile the model, tell it which optimizer we want, and which loss function we're going to use. There are a couple different loss functions you can use. We're just using this one. That doesn't mean you can't use another one. All right, there's our function. No errors so far. Let's go. So let's try out our model. We're going to get the generic unattacked model. Create model, given atom optimizer, an array Lu activation parameter. Got to fit it to the train images, the train labels. We're going to give it 10 epochs, and its validation data is going to be our test images and test labels. All right, let's run this, see if there's an error. Oh, yep, I misspelled RayLu. All right, what else do we got? Let's see. Oh, was missing a parentheses and missing another parentheses. There we go. There we go. There's our base model. Now let's see how well this model did. Let's see, so we get a baseline accuracy of 87%. We could do a lot better, but that's because we're not using all of the data. All right, so now let's poison this data set. We need to be able to give it the data set, give it the label that we want to target, and then which label we're going to replace it with, and then how many instances we want to replace it with. So let's add the metadata. All right, we need a counter. So for all of the training labels, we are going to check if the label is the target label we're trying to replace, and also make sure that we haven't replaced more of those instances than we wanted to. Part of this would just be maybe for covering your tracks. If there are no 5s in the entire data set, that's going to be a little bit suspicious. All right, so counter pass, return the labels that are poisoned now. Yep, all right, so we're going to print label 0 and 1. And we're going to replace whatever 0 is, which is the 5, with what 1 is. So our poison labels is our function poison data. We'll give it the train labels. We're going to give which one we're looking for, and then which one we're going to replace it with. And then how many we're going to do. We're going to do 50. We have about 1,000 images, and each number for the MNIST classifier data set makes roughly about 10%. So we would expect about 100 5s and then 100 whatever the other one is. All right, so let's create the model. Let's predict it. Now let's count. We would expect the one that we replaced it with to be very few, and then the ones that is the replacement to be much higher than that, roughly 10% or 100. So let's print that out. It's 5, or if it equals 1, which is what the second one is. All right. So let's see. All right. We got any errors? Let's see. Missing a parenthesis, or put an extra parentheses in there. It's training. Then we got 5, which we're replacing with the 0. You can see our model accuracy went down from the 87% to the 83%, and we see 51 5s and 139 zeros. We would expect to see 100 5s and roughly 100 zeros. You can see by poisoning the data, even though we didn't poison all the data, we can make the model much more biased to the 0 and biased away from the 5. There's still enough there that it might go undetected, but it's enough that we can bias the model to behave how we want to.